Good morning and good evening, everyone. Now, as a part of our today's session, we'll be understanding what is deep learning and we'll get some general intuition about deep learning. We'll proceed ahead and get some high level understanding about image processing, and then we'll do a hands-on session where we'll make use of brain tumor detection. That means I'm having the set of images where the images belongs to the person having a brain tumor, and the another set of images which do not belong to the brain tumor, and I'll be training my deep learning model to differentiate between those two classes. And to do this, we'll make use of the technique of transfer learning. And this transfer learning that I'll be applying, I'll be making use of CNN architecture, that is convolutional neural network. Okay, so that's the agenda of today's session. So introduction to deep learning. So why do we have to use this deep learning? Why can't I use a machine learning or any other tools and technology which is available out there? And why do we actually use this deep learning? And why do we see like lot of companies using this deep learning? The reason because the traditional algorithms that we have, these traditional algorithms will become stagnant. I mean, after some time, the accuracy that we would get from the models will not improve when there is increase in data. But with the help of deep learning, we'll be able to achieve better and better accuracy even when there is an increase in the amount of data. So that's the advantage of using this deep learning, guys. And we see this application of deep learning in many fields, be it in speech recognition, image classification, natural language processing, many more. So we see this application of deep learning in wide variety of spaces. And whenever someone talks about deep learning, you'll see a figure that would look like this. So a deep learning, or whenever someone is talking about deep learning, it would look something as, okay, there will be something as an input and there will be something as an output. And in middle, we'll have something as an hidden. So these three parts that you would see, input, hidden, and output. So these three parts are the components of any deep learning neural network. Now, through this input layer, we'll receive the input, and my computation would happen in my hidden layer, and in my output layer, I'll be displaying the output. So that is how we would do in case of deep learning neural network. I'll get the data from input, I'll process in my hidden layers, and whatever the data that I'll process, I'll give as an output using my output layer. Now that's the high level view if I want to talk about deep learning, guys. Okay, now this connection that you see between the layers, so this connections represents, or this arrows represent the connection between those respective layers. And if I have like connection between like every neuron, so individual component that you see over here, so this is called as neuron. So if I have a connection between one neuron from previous layer to every other neuron in my next layer, then we are going to call this network as a dense network. Okay, and the reason that we have used this kind of a structure, because this deep learning has been developed to, or this deep learning has been made, what I can say, like it has been made as a, it has been developed after the like influence, or after we have, or like we wanted to imitate the working of the human brain. So because of that reason, so we wanted to have some kind of a processing system which will actually mimic the way we human learn. So just like we humans have our sensory organs to receive the data from the outside world, or to feel the things that we want to see in the outside world, so we have the input layer, okay, in our deep learning neural network. And just like we in our brain cell, we have numerous neurons that we have, that is called as biological neurons. Just like we have millions of neurons in our deep learning neural network, we are going to have this kind of artificial neurons. And just like we respond to it after we process the information in our brain, like in other words, we are going to give the output, right? So in the same way, in my deep learning, I'm going to have my output layer. So deep learning is an artificial intelligence function that imitates the working of the human brain in processing the data and creating the patterns for use in decision making. Okay, so that's what deep learning would mean. Now let's get some general intuition behind this deep learning, guys. So as I mentioned already, the way this deep learning or this concept of deep learning came, so it's inspired by the way that we have in our human brain. So just like in my human brain or a single cell of a neuron, it will have dendrites which receives the sensory organ information, and I'm going to have some nucleus which processes the information that I receive through dendrites. And this axon is nothing but the layer, I mean, like whatever the information that gets processed in the nucleus, it passes through the axon, and through the axon terminals the informations would be sent out to the other biological neurons. In the same way, it is just a representation. If I take a single neuron in my artificial neural network or a deep learning neural network, I'm going to have my input layer in place of dendrites, and just like we have a nucleus which processes the information, we are going to have some kind of a mathematical function inside a neuron to process this incoming data. And just like we have axon terminals to give the output and which decides whether I should trigger my next neuron or not, in my deep learning neural network we are going to have my output layer, and we are also going to have an activation function which decides whether I should uh, process or whether I should send out this output from my neuron or not. So that's the comparison, or that's how we actually compare it between our single human brain, a single brain cell, and a single artificial neuron. And this single artificial neuron, we sometimes we also call it as a perceptron. Okay, so coming to the mathematical intuition behind it. So suppose if I have inputs like this, x1, and this should be x2, x3, and x4. And let's suppose I'm having the weights as W1, W2, W3, and W4. Now to process this incoming data, I'm going to do two things over here. One is the summation. That means I'm going to multiply my inputs with the weights, and along with this, I'm going to add my bias term. So this activity is called as summation with bias term. And on top of this, to decide what is the output that I should give, I'm going to have an activation. So inside a single neuron, two things takes place. One, summation, and the another thing is activation. You can think of this as what would happen in the single biological cell that is inside the nucleus. And this activation you can think about as what would happen at the axon terminals. Okay, so like if you're someone from the biological background, you can do this linkage. Okay, and don't worry guys if you have not been following along with the comparison between biological neurons. So only thing for you to remember is whenever I'm processing the information for a single neuron, to get the output, I'll take the dot product between my inputs and the weights, and I'm going to add a bias term. So if I want to represent it mathematically, sigma of I is equal to 1 to m, assuming that I'm having m inputs. Okay, and inside the parenthesis, I'm taking the dot product, that means wixi, plus bias term, that is b value. Okay, and after the output we are going to apply the activation function to decide what should be the output. Now this computation that you're seeing for a single neuron, the same computation would happen on a bigger neural network as well. So I mean, whatever the computation that you had seen in the previous slide, the same would be applicable here as well. The same thing applies to every neuron in my hidden layer. Now in our scenario, we'll be making use of our deep learning neural networks to perform the image processing. That means for working with X-ray image. Now let's see how we can do that and how we can actually perform this with image data using our deep learning. Now, in order to work with image data, we are going to make use of an architecture that is known as convolutional neural network. And the reason that we would prefer using this convolutional neural network, because if I'm using a traditional deep learning neural network, whenever there is an image, for example, whenever we are dealing with an image data, obviously I cannot expect every object is present in the same place in an image. Just to give you an example, I can have a image where if I'm having a tree over here on my left side of this image, and I can have one more image where my tree is present over here. Now, if you look at it, like in both the places or in both the images, I'm having the same object, that is tree. But what happens if I'm making use of normal artificial neural network is, whenever I'm having this image data, where my object is present in different parts of the image, at each time this is going to treat it as a separate object, and the deep learning tries to find features, and it creates lots of features during the learning. And because of this, we are going to have lots of issues while working with image data, which is an unstructured data. Now, in order to avoid that, we make use of this convolutional neural network. Now, this convolutional neural network will work in a different way. Like, to give you an intuition, we'll take a picture in our mobile devices. So do you agree with me, guys? So normally we'll just take a picture in our mobile devices. Now, after we take the picture, what is the next activity that we do? Like when we take a selfie in our picture, uh, before we share it on a WhatsApp, or before we share it on our Instagram or on Facebook account, why do we actually do it? Yes. So we actually are going to make it better. I mean, to make the object in that image to look better. So how do we actually do it? So we are going to apply various filters. So I'll readjust the image. I'll do some sort of activity over there. And after I do that activity, I'll be increasing the brightness of the object that is present in the image. And sometimes I'll give the special effect for that image. Now, that very thing that we have done over there, that is to apply the filters. So that is what would happen mathematically when I talk about convolution operation. So convolution operation means adjusting or I can say modifying the pixel intensities for a given input image. So that is what it would mean by performing the convolution operation. Now, when we apply our image data on our convolution neural network, what would happen in the backend is, my neural network is going to apply various filters in the backend. And by applying various filters in the backend, it is going to learn the important features for a given input image. Now, in this example, I'm having an image of motorboat. Now, I'll have some kind of a filter. My convolution neural network will have this filter, and it will use this filter and tries to apply some of the special effects so that it can learn, okay, if this is a motorboat, so how does its edge would look like? And if this is a motorboat, how does its top structure would look like? It learns to identify various components for a given input image by doing this operation, mathematical operation, that is called as convolution. Okay, so in reality, we will have multiple convolution layers. And when I say multiple convolution layers, I'll do this feature engineering activity multiple times so that I extract lots and lots of information from a given input data. In case of convolution neural network architecture, we'll have a convolution layer followed by a pooling layer. And this pooling layer is like a layer which will help me in compressing the information that I'm having as a result of this convolution operation. And once I have this series of convolution layers, pooling layers, convolution layers, and pooling layers, this will be connected to a fully connected layer, which will help me in finally identifying the features that are present in my given image. Okay, now that's the intuition behind our convolution neural networks. Okay, now for the easier understanding, you can think of this convolution neural network working on the images as template matching. So I'm having an image, and let's say I'm having a template. I'll move my template from left to right and top to bottom, and I'll try to uh, check, okay, whether this given whether it is matching my template. So this is very like, you can use this image, or you can use this as a very high level understanding as how this CNN would work, guys. Now, as I mentioned already, whenever I'm performing this convolution operation, I'm going to modify the pixel intensities in a given image. Now, in CNN, we are going to call it as convolution filters. Now, just like we have the filter in our mobile phone, so in the same way, so we are going to apply the filter on a given image. Now, when it is applying the filter on a given image, what it would actually do is, it would actually place a filter. So you can think of this filter as some kind of a matrix, a two-dimensional matrix of the shape that we would specify whenever we are working. And we'll place this filter on top of our pixel area. And we are going to take the dot product between those two regions. That means 0 into -1 plus 75 into -2 plus 80 into -1 plus 75 into 1 plus 80 into 2. So plus 1 into 80. So if we do this activity, that means like if we simplify this, uh, if we simplified everything, we are going to get the output as 85. So what we have done over here is we have modified this particular pixel region, which was 80 before, into 85. Now this is what would happen whenever we perform a convolution operation on a given image. I'm going to change, or I'm going to modify the pixel intensity of that particular pixel in an image. And to do this, I'm taking the dot product between my filter, and sometimes we also call it as kernel as well. I'm going to take a filter or a kernel, and I'm going to take the dot product between my image region with my kernel region. And once I do this activity multiple times, I'll be changing the pixel intensities of those images. Now I'll use those changed pixel intensities for my future learning in my deep learning neural network. And once I have done this sufficiently, the common thing that we would perform is we are going to send this output of this convolution filters into a pooling layer. Now, in case of a pooling layer, it is very simple, guys. You can observe this slide for intuitive understanding. Now, there are two types of pooling. One is max pooling, and another one is called as average pooling. Now, this slide talks about an example for max pooling. So what we do in case of this max pooling is, for a given input image, we will have some or the other pixel intensities. Let's assume these are the pixel intensities that we have for a given input image. Now, while performing this pooling operation, we'll make use of a concept called pool size. Okay, pool size, and sometimes we also call it as window size. And this would most probably have the window size of 2 by 2, unless and until we have researchers finding and we have for a different network. In general, we will have the pool size of 2 by 2, and we'll make use of stride as 2. Okay, so this is what happens in the backend. So we will use this pool size of 2 by 2, which is a matrix, and we'll place on top of our input image. Let's say if I place my input image over here. Now, after I place my pool, that is select the region of 2 by 2, I'm going to see what is the maximum value of the pixel intensity that is present in my given input region. Now, in this region, the maximum value that we have is 6. So 6 is given as an output over here. And similarly, I'll place my pool over here, that is my pooling window over here. And in this 4 by 4, in this 2 by 2 region, the maximum value that I'm having is 9. So 9 will be the output from this region. I'll place my window over here. Even in this scenario, maximum value is 9. So 9 will be placed over here. And for this region, you can observe, see, this is the maximum value, and 8 will be 8 is the next value, guys. Okay, now here I have mentioned something as stride. Okay, so stride is nothing but the step size. Okay, so it would mean that like by default stride is equal to 1. Now if I, like, when I say stride is equal to 1, I'm going to move 1 pixel at a time, moving from left to right and top to bottom. Now if I have stride is equal to 3, I'll skip 2 steps and then select the third pixel while selecting my pooling window. So that is the whole intuition behind working with pooling layer. And one more thing, if you had observed in the previous slide, whenever we are performing this convolution operation, if you observe at the end, I'm losing a dimension along each axis. See, if you observe, my input is of the dimension 5 by 5. Now, as a result of applying my filter of the size 3 by 3, I am losing the dimension like this, like I'm losing the dimension across each axis, that is X and Y axis. The reason that I'm losing this dimension because my this kernel is of the shape 3 by 3, and I can place my kernel at the center of the 75, 80, 80. So I can place my 3 by 3 kernel only in my highlighting region. I cannot place my kernel at the outside region. Now, since I'm unable to place my kernel in these outer regions, I'm actually losing the dimension over here while performing this convolution operation. Now, in order to avoid losing the dimension while performing this convolution operation, we are going to make use of a layer which is called as padding layer. Now, if you observe this, see, I'm having my original image, which is of the shape 5 by 5. Now I have added a padding layer over here. So this shaded portion that you're seeing for a given image, so these are the extra padding that I've added, where the pixel intensities of those region will be equal to 0. Now by adding a padding layer over here for a given input image, I'm not losing the dimension even after I perform this convolution operation. So that's the concept behind this padding layer. So we have learned about 3 important layers: convolution layers, and another thing that we had learned was this pooling layer, and next one is padding layer. Now, in a given convolution neural network architecture, we'll have series of convolution neural networks followed by pooling operation, followed by convolution operation. And once we are done with applying the series of convolution operation, we are going to perform a flattening operation. Now, this flattening operation is nothing but converting my multi-dimensional array into a single dimensional array. That is the intuition behind flattening operation. Just to give you an intuition, suppose if I'm having an array which is of the shape 5, 5, 5, which is a 3-dimensional array, the resulting of my flattening operation will be, it will create a single dimensional array where the total number of elements will be equal to 5 into 5 into 5. I think it will be equal to 125 elements. So that is what would happen when I apply this flattening operation for a given pooling layer. And then if I want to show to you at a high level as how a common convolution neural network would look like. So I'll have my input image. On my input image, I'll perform series of convolution operation. Okay, so in this scenario, I have used the kernel of 5 by 5, and because of this, I have my input image, which was of the shape 28 by 28, has been changed to 24 into 24, and I'm having N1 channels, which means I'm performing convolution operation N1 times. And after I perform my convolution operation, I'm performing the max pooling operation with a max pooling pool size of 2 by 2. Now, as a result of applying this max pooling operation, so the dimensions of my image have been reduced to 12 by 12. And on top of this, I'm performing again convolution operation. And this time it is also of the shape 5 by 5 kernel. And then this is the resulting shape, and then I'm performing my max pooling layer, and whatever the output that I'm getting over here as a result of this max pooling operation, I'm converting into a flattening layer. And once I convert into a flattening layer, I'm connecting all those neurons into a fully connected neural network, which is a dense network. And then I'm going to have my output layer. Now, based on the activity that I'm performing, let's say if I'm performing the multi-class classification, I'll have the activation as softmax. If I'm performing a binary classification, I'll use the activation of sigmoid as per my requirement. Now, that is the high level intuition behind given any convolution neural network. Now, in our webinar, we are going to perform this tumor detection using this convolutional neural network. Now, to perform this brain tumor detection, we'll make use of a concept that is called as transfer learning. Now, in case of transfer learning, what we'll be doing is we'll make use of the model which has been already trained for a given specific task, and we'll use the already trained model and train it on a specific data set which we are interested in. So an example can be something like this. Okay, suppose if I'm having a requirement to detect whether my given input image has car or a truck. Okay, if this is my task that I want to do, now what I can do is I can make use of a deep learning model which has been already trained on a different data set, but for the same type of data set. An example can be something like this. I am already having a deep learning model which has been already trained on a data set which is an image data set, and this model has been trained to classify for a given image whether it belongs to cat or whether it belongs to dog. Okay, so let's say this is the requirement that I'm having. Now this is my existing model that has been trained. Now what I can do is I can use this deep learning model which can identify whether a given input image has cat or dog. I can use this model, and on top of my already learned model I can create some additional layers, deep learning neural network layers, and train on my new data set, that is new data set, to identify for a given image whether it belongs to the class of car or truck. So that is the advantage of using this transfer learning. Now by doing like this, we will be reducing the amount of time that we have to spend on training, and we are going to get higher accuracy while performing the training, guys. So that's the advantage of using this transfer learning. So this slide also gives more intuition behind this transfer learning. So let's say I'm having data set one where I've trained my machine learning model one, and I'm having my data set two where I've trained my machine learning model two. And in case of transfer learning, we'll make use of the learning that we had from the model one, which we got by training on top of our data set one, and then use that learning to train a new data set two. Now, in our scenario, we'll make use of the convolution neural network architectures, and some of the common CNN architectures that we have is like LeNet architecture. So in case of LeNet architecture, we'll have my input image, and this is how various layers that we have. So like we'll have a convolution layers, series of max pooling layer, and then convolution layers, and so on. And likewise, if I take another example of mobile net model architecture, this is how the architecture of my mobile net model would look like. So each of my architecture will have its own settings. When I say settings, it expects the input in its own shape, and it has its own set of convolution layers, and it has its own set of dense layers, and it has been prepared to do a specific task. So what we'll be doing in our hands-on session is we'll make use of a convolution neural network which has been trained on a different data set, okay, that is on an ImageNet data set, and we'll make use of the pre-trained model, and using that pre-trained model we are going to perform this activity of brain tumor detection. Okay, all right, now to get started, I'm just loading my data set. The data set that I'm having, it's already present in my Dropbox. So I'm loading directly from my Dropbox. So this is going to load my zip file, which is present in my Dropbox, and it is going to do the unzip. I'm just using my Linux command, and I'm removing this zip folder so that I'll be saving the memory when I'm working with Google Colab instance. Okay, so this has downloaded and it has also performed the extraction. I can verify it by clicking on this file explorer. Okay, so a new folder has been created. So this folder is brain tumor dataset, and inside this folder, I'm having two subfolders, brain tumor and health is healthy. And if I expand this brain tumor, so it has some set of data set. See, like I'll just download an example image, guys. Okay, so this is an example image which belongs to the cancer class, which means this image or an X-ray image has a label of cancer, which means okay, this belongs to the cancer patient. And I'll just open and sample data from an healthy images. Okay, so this is an example image, example X-ray image where it belongs to the healthy person. Okay, so here I've got some question over here. So how to handle the imbalanced real-time data set using transfer learning? So when you're having an imbalanced data set, we'll try to balance it out, or we'll try to add the weights to those classes. So you can work on it. We can work on it depending on the application that we have. Now after this, I'm just importing my various libraries, and I am uh, setting up my data. So I'm just setting as, okay, where exactly is my data set is present. So I'm just specifying what is the folder path, and I'm just counting how many number of images that I'm having in my given data set. So in my case, I'm having 2513 images belonging to the brain tumor and 2087 images belong to the healthy patients. Now, one common activity that we do whenever we are performing the training is we are going to split our data set into three parts. So one is training data, another is validation data, and the another set is test data. We'll make use of our training set and the validation set during our training. And after the training is complete, we are going to make use of the test set to see as how our data set, how our model is working. Now, an example can be something like this. So like for training, you can think of it as a textbook where students use it to learn. And for validation, you can think of it as a preparatory exam to identify, to measure as how the students is performing. And test set, you can think of it as a final exam, as a final validation where we would use to measure as how the student is performing. So in the same way, to be able to have those data set, we are just creating the three subfolders as training set, validation set, and the test set. All right. So I'm just creating three subfolders, and I'm just copying some of the images to those specific subfolders. Now, after I have executed those, it has created three folders over here: test, train, and validation folder. So I can access the folders of this train folder to perform the training, and I can access this test folder to perform the testing, and I can access the images in my validation to perform the validation for a given image data. Now to perform the training, in this scenario, we'll make use of Tensorflow Framework. Now from Tensorflow, this Tensorflow actually provides a high level API which is known as 𝐄𝐝𝐿. So from 𝐄𝐝𝐿, I'm importing the various layers as per our requirement. So these are some of the layers which I'm importing. I'm defining my model as sequential, where I'm placing one layer next to another, and I'm loading some of the image pre-processing function that we have, which will help us in loading the data, that is our image data. So I'll load my required libraries, and this is going to take care of creation of my model. So for creation of model, I'm creating my model as sequential. Now to give you a high level understanding as what is sequential model is a type of a neural network where I'm having one layer stacked next to each other. So what this would actually mean is I'm defining my model as sequential, and I'm saying it as model.add conv2d. So my first layer is a convolution layers, and this takes the input from the shape of 224, 224, 3. So let's say this is my input. This has the shape of 224, 224, 3, and this is connected to a convolution layer. And then this is connected to another convolution layer, which has filters of 32, and this is followed by max pool layer. So if you look at it, I'm placing one layer next to each other. Hence, we call this model as a sequential model. I'm defining my model, and I'm stacking one layer next to each other, that is convolution layer, max pool layer, and so on. And at the end, I'm compiling my model, which is a mandatory step that we have to do to tell our network, okay, as how it has to train during the training. So in our scenario, the model has the loss function as binary cross entropy, optimizer, which is the learning algorithm, as Adam, which is one of the most commonly used learning algorithm, and the metrics that we have is accuracy. So if you're new to TensorFlow, I completely understand most of these terminologies would mean as a foreign language, but just be with me, and just be with me till the end. You'll see as how the deep learning model, which we actually train with few lines of code, can or has the ability to differentiate for a given data, guys. Okay. All right. So now that this would actually display the model summary, how the shapes are getting changed for given input data. Now, as a part of next mandatory step, I'm trying to create my training data generator object. The reason that this is being created because my data set, or during the training of deep learning, the normal thing if I don't use this data generator means it is going to load my entire data set into my RAM. So in order to avoid that issue, the reason that we want to avoid this issue is, in our example, I'm having my total image size of 800 MB or something. Okay. Now I might not have issues when I'm training on my RAM because I'm having close to 13 GB of RAM. So even if it uses 800 MB, it won't be a concern. But imagine this, I'm having around 20 GB of image data. Now I cannot load all those 20 GB of my image data into my RAM and start the training. It would definitely cause memory issues for the processing. Now, in order to avoid that, what we do is we are going to create this training generator objects, which would actually help us in loading the data in the batches. So each time using my generator, I'm going to load the data in the batches. An example can be, in our scenario, we are taking 32 images. So I load 32 images from the hard disk to my RAM. I'll process those 32 images, then I'll delete those 32 and I'll load a new batch. So by doing like this, I'll be efficiently freeing up my RAM, and my RAM will be completely used for processing the information while that is during the computation and not on the data storage. Hence, I'm creating my image data generator, and I'm also specifying as how it has to flow from the directory like this. And I'm doing the same for my validation data and the test data. Now, in order to verify as how my model is performing during the training, I'm going to make use of model checkpointing and the early stopping. Now, using this technique, I'll be able to save my model once it has reached the good accuracy, and I'll not be losing it after it has left that good accuracy. So that is the reason I'm making use of this callbacks. And once everything is done, I'm going to perform this fit generator. So using this fit generator, we'll be able to fit the model with our data. When I say fit the model, I'll be training my deep learning neural network using my model. Like I'll be training my neural network to learn the various features that are given in the image, and then we are actually saving that model in the backend. And once we have saved it, we are actually going to load the model, and then we are going to check the accuracy as how our model is performing, and finally we'll be able to test the model as how our model is performing on the data set which is not seen yet. Okay, so that is how we would do, guys. Since it's training a deep learning model, it will take a while for it to complete. So the training is progressing for me. So here, I'll just show you as how to actually read these logs. Okay, so the accuracy at start is 0.44, that is 44% accuracy. And then as we could see, with every epoch in the training, we could see that the loss is getting decreased and the accuracy is getting increased. Okay, so that is the best thing about training our deep learning models, guys. We can train our deep learning models to learn on a given data. Now in our scenario, like we were able to reach the accuracy of 74.61%, and since it did not reach further, so we just stopped our execution, and we have made sure that we have saved our best model. Okay, so we have saved our best model. Now what we can do is, after we have saved our best model, we can load this model using a load model method that we have inside our TensorFlow, and then we can perform the evaluation on a new data. So in our scenario, the evaluation on the test data that we are getting is 72% accuracy. And if you visualize as how the accuracy that we are getting during the training, okay, now I think it is saying as I just have to change over here. Okay, let me just give a different image. Okay, So I've given an image which belongs to the class of cancer, and I have the output that says as the MRI image is of brain tumor. Okay, so like that's what we have done, guys. So I the only thing that I want you to change is in the last cell for the path, make sure you replace it with this code to test it whether you're able to get this output or not. Okay, the accuracy that we would get is obviously will not be 100%. There could be a scenarios where even though my true values of my given input data would belong to the cancer, I might get an output as as a healthy. The reason because the model with which we have trained, which have just trained for only few minutes, and we have the accuracy of 74% on our validation data. Now to increase it, so obviously we have to train for longer periods. We have to uh, like increase the complexity of the model, use multiple layers, and sometimes if it's still not increasing, we can just increase the data images that we image data set that we have, and then we can see whether our model accuracy is getting increased or not. All right, folks, I hope this session has been helpful to you. Thank you for joining with us.